really bad job pacing myself in the third period. I'm gonna do better today, this period. But today I just want to focus on like practicing generating these things called Taylor and Maclaurin polynomials of this certain functions. To kind of start us off again, so Taylor and Maclaurin polynomials are basically the same thing. The name is just coming from a Maclaurin polynomial is going to be one that is always centered at 0. Taylor is going to be one that's centered at any value, technically also including 0, so you could make the argument that all Maclaurin polynomials are also Taylor polynomials. But when we're talking about these, what are they basically representing? They're basically an infinite polynomial that represents a function. So there's different things that we're going to eventually do with them. We probably won't get to it until Friday. So I will say like the notes are still going to feel weird today and tomorrow as we just are like still adding to like kind of foundation. The fun stuff, and fun for me, maybe not fun for you, is like what we'll get to Friday when we start like doing things with them. The first thing that the AP exam is going to require you to understand, and what we really do need to understand kind of moving forward, is how to create a polynomial when given the function. So that's going to be the first example that I wanted to kind of look at. And so I'm taking that series and kind of expanding it into a table. So Maclaurin polynomials and Taylor polynomials, just like Euler's method, is a way to approximate a function. So similar to how Euler's method had like a table format you wanted to memorize, creating both Taylor and Maclaurin polynomials, you do want to have some sort of like table to look at. I kind of do the grids because they do kind of take a little bit more space than just finding a number. But the 4 columns that you want to think about having is you're basically going to have a column for the degree. So that's going to be like the largest exponent we end up seeing. You're going to have one representing the nth derivative. So we know that when we're seeing where these came from, we just kind of hit the derivative over and over and over again. You're going to figure out what you're evaluating it at. So we're going to evaluate it at whatever the center is. Could be 0, could be another number. And then really the most important column is going to be just us creating the terms. This comes from what's inside that sigma notation for the Taylor and Maclaurin polynomials. And so if I'm looking at this problem, we want to create a third degree Maclaurin polynomial for y is equal to e to the 2x. I wouldn't have to really say centered at x equal to 0 because Maclaurin means centered at 0. So how is that going to affect my chart? That basically means when I find all these derivatives, I'm going to plug in 0. And then once I find that value, divide it by n factorial, and then like I have x minus the center raised to the n. When we are creating a third degree Maclaurin polynomial, the highest exponent we'll have is a 3. So it will be a cubic function. And the idea of what we're creating is we are finding a polynomial that is going to approximate the graph of y is equal to 2x for values close to 0. So how I do this, I go ahead, we're always going to start at 0. So I'm going to start at 0, 1, 2, and then stop at 3, since we're just looking for a third degree polynomial. Degree of 0 is going to be your original function. So my original function would be e to the 2x. And then you just want to keep taking the derivative of that over and over again until you have filled up the number of rows you need. So like when I say n is equal to 1, that is like the first derivative. Make sure we use the chain rule. That becomes 2e to the 2x. When I see the 2 there, that's looking for the second derivative. So I take the derivative, chain rule again, 4e to the 2x. And then that 3, third derivative, so that's going to be 6e to the 2x. So those are my derivatives. 8, I can multiply, I promise. 2 times 4 is definitely 8. Erase, there we go. 8. So then when we find the derivative correctly, now you want to plug in the center, and that's what's going to generate a number we're going to use for our coefficients. This one is centered at 0. Again, that would change depending on what we're centering it. And when we say the center, I want you to think about like that's where the polynomial is going to be good. So like close to 0, this polynomial is going to look just like e to the 2x. Further out from 0, it will look less and less like y is equal to e to the 2x. So plugging in 0, we get e to the 0th power, which is 1, 2, this is a pretty easy one to do, 4, and 8. You can kind of imagine the more complicated functions have some more complicated derivatives to find. And then we're going to use those numbers to find the terms. So how do I find those terms? The number you find here, you're going to divide it by the degree factorial. So that's going to be the 0 degree factorial, and then that's going to be x minus 0 to the 0th power. And obviously you probably wouldn't write all of that down. That is just going to be equal to what? 1. Then for the next one, this is your first degree, so I'm going to have the 2. This was the first degree, so divided by 1 factorial. X minus the center of 0, this is to the first power. Simplifying it, you would probably just write down 2x. Repeating that, so we got the second derivative was 4, divided by 2 factorial. That's going to be x minus 0, this is the squared term. Well, 2 factorial is 2 times 1, so 4 divided by 2 is 2, and I get 2x squared. And then last one, we have 8 divided by, this is the third degree, third factorial, x minus 0 cubed. Simplifying it, 3 factorial is 3 times 2 times 1. So I might be like, okay, 8 divided by 2 is 4, so I have 4/3 x cubed. What have we found? That last column are representing the terms. So I'm going to scroll down to give me a little bit more space. We have basically found, I can fit this all on one screen, that this is a Maclaurin polynomial for y is equal to e to the 2x. So we have found that e to the 2x is approximately, I'm going to use a capital P with a sub 3, representing a third degree polynomial. So it's going to be p sub 3 of x. And then I just have my terms. So we had a 1, a 2x, a 2x squared, and then a 4/3 x cubed. And I do want to kind of look at that statement. So we are saying that the graph of e to the 2x, the function e to the 2x, can be approximated by this polynomial you see. It is a degree 3 polynomial, as long as you are close to 0 for that function. And so we can do different things with that. Like if I wanted to find a decimal approximation for, say, e to the 4th power, I could plug in 2 for x and do that. If I want to approximate the derivative of e to the 2x, I could take the derivative of that polynomial. If I want to approximate the integral of e to the 2x, it's going to be equivalent to the integral of that polynomial. Thankfully, we live in modern times and we have technology, and I do think seeing the graph of this is pretty cool. So this was the graph of e to the 2x. We know what that graph looks like. It's an exponential function. These are the terms of my Taylor polynomial. So we have a degree 1, and I'm actually going to change the scale of this one. There we go. So we see it's an exponential, and we were centered at 0. Let me fix that. So there was the first term. The first term was just 1. That's what the Taylor polynomial looked like, nothing too exciting. The degree 1 Taylor polynomial, that would be the first 2 terms. The degree 1 polynomial is always going to be a tangent line. There's the degree 2 one. You can kind of see it starts modeling close to that function. What we found was the degree 3 one, which is a cubic function, and you can see close to 0, they're pretty much identical. As you get further and further from 0, obviously they start to kind of fall apart. So like kind of like a big idea, like we want to have a more accurate approximation, we just need to keep adding more terms. Like if we wanted to do another row, there is the degree 4 Maclaurin polynomial. There is the degree 5, which is as I went, and you can kind of see it's almost identical until you start getting further and further from 0. So you can imagine, like, since with these being infinite polynomials, if you could use all infinite terms, it would be the exact same function, which is kind of like the big idea with using these Taylor polynomials. So note-wise, and things that I do want to kind of be clear, like any function can be written as a power series, whether you're using a Taylor series or a Maclaurin one. It can be written as a power series. It should probably be a little bit more clear. As long as you can like find a derivative, then it could be written as a Taylor or a Maclaurin series, which has lots of applications. Probably more applications if you're taking math in the early 1900s instead of 2021 when we have graphing calculators. But it was super useful in like programming how calculators work. Like when you type e squared in your calculator to get that decimal, your calculator doesn't know e to the x. Your calculator actually has programmed into it. It's not exactly a Taylor polynomial, but it's a relative of the Taylor polynomial, and that's what it's using to do all the math. So like it is important. You didn't realize you needed them, but why our graphing calculators work the way they do is because of these things called Taylor series and Maclaurin series leading into the polynomials. So go ahead one more for me, because I know this does get kind of tedious, but I want you to get kind of used to it. Go ahead and try this one for me. So I want you to use a second degree Taylor polynomial for y is equal to the arctangent of x. This will probably be more tedious because the derivative is kind of annoying to find. We are going to center it at 1, so it is going to be a Taylor polynomial, not a Maclaurin one. And then that polynomial you find, you're going to use it to approximate the arctangent of some point. And we'll actually kind of see, like we have calculators where we have to see how like far off we actually are. But go ahead and generate that table for me, and then use that polynomial to find an approximation. And I will say when you're making that table, just make sure you use for that second derivative, you probably want to make sure you use the table. And again, for the most part, when you're doing these, you're always going to start at n is equal to 0. That's going to be like the initial function, which will give you your first term. And then it will always kind of tell you which type of degree polynomial you use. So it normally won't say like find like the first 2 terms. It'll say something like find the degree. So it might be, if it says like find 2 degree, it might end up being like usually a 3-term problem. So we can find our derivatives. We have the initial function, arctangent, its derivative 1 over 1 plus x squared or x squared plus 1. Taking the derivative of that, either quotient rule messy or rewrite it and then use the power rule with the chain rule. This one is centered at 1. And again, what that means is this function is going to be closely matching arctangent around 1. So plugging it in, the arctangent of 1 is pi over 4. 1 over 1 plus 1 is 1/2, and then I have like negative 2 over 4, which is negative 1/2. And then we're using that number to do the final coefficient. So remember, we are always dividing by the degree factorial. Show as much or as little as you need to, especially these first 2, which will always have like 0 factorial in it and 1 factorial in it. So many of you probably won't need to show all the steps for those first 2 rows. Our first term ends up just being pi over 4. Our second term is this 1/2 x minus 1. And then for the degree 2, so I have the second derivative at the center divided by 2 factorial x minus 1 squared. So that's going to be negative 1/4 x minus 1 squared. Make sure you always write what the polynomial is, so don't leave it in that table. What is this polynomial? Basically, the graph of arctangent around x is equal to 1 is approximately this 2-degree polynomial, second-degree polynomial, with terms of pi over 4, 1/2 x minus 1, and then negative 1/4 x minus 1 squared. And then we can use that polynomial, because basically the idea is, if this polynomial is modeling arctangent around 1, plugging in values close to 1 into the polynomial are going to be fairly close to the value of arctangent at that same value. So we can say the arctangent of 1.2, plugging it in, we would have pi over 4 plus 1/2. 1.2 minus 1 is 0.2 minus 1/4. 1.2 minus 1, 0.2 squared. You can leave your answer like that. I am going to type it in the calculator just so you can actually see how kind of cool how close it actually is. So I have pi over 4 plus 1/2 times 0.2 minus 1/4 times 0.2 squared. And what this ends up being equal to, kind of going out to some decimals, is we have 0.8753981634. And I wrote out that many decimals because the actual value, again, we live in 2021, so I can find the actual value, and we can see how close we are. Typing in just the arctangent of pi over 4 in my calculator. The actual value is 0.665773775, which you may argue is around that's not close. But to me, that is pretty close, depending on what we are kind of looking for. And of course, we can be more accurate by finding like more and more terms. Seth, you have your hand up.
You said the actual value of arctangent of pi over 4.
Oh, that's why that looks so far off. Let me actually find the arctangent of 1.2, and we'll be even closer, and that will be even more amazing. So yeah, cool. Let me actually do the arctangent of 1.2, which will be even more incredible, and not even that far off, because it becomes, yeah, what I actually expected, 0.87605.80506. So pretty much like, you could probably argue those decimals are close enough for a lot of applications, again, in a world before calculators. So where are we kind of going with this? Eventually, we are going to be doing calculus with these power series. Like, how can we take the derivative of a power series? How can we integrate a power series? How can we generate a power series quickly? For example, if I said, hey, let's make a Taylor polynomial for the function x squared times the arctangent of 1 over x, no one wants to sit there and make a table of that function. It has like power rule, chain rule, product rule, it's gross. So what we can do is there are going to be some special power series that we are going to memorize and use those to create some of the more complicated functions. So what I want to kind of spend the rest of the period with today, and again, I won't get through all of them today, but just kind of go over some of the key power series we have, some of like our basic functions, see what the series look like, see if we can kind of come up with a formula for them, and then hopefully by Friday we can actually start doing things with them. So if you're following along in notes, I'm going to jump ahead now to the slide that says the big 5 with a bunch of exclamation marks on it. Don't worry about writing those now, like we're going to see where all of this comes from. But basically in AP Calculus, and really like in upper level math in general, there are 5 main power series that you need to like know and like basically love. Like you need to memorize them, and that's what we're going to kind of talk about today. Again, don't rush to write those down right now, because we're going to actually go through and like derive each of them. Because like one thing we'll notice is like, if you can't memorize them, you just have to like quickly be able to figure out what it looks like. And the 5 main series that you have to know is going to be one that we call the geometric series. We have the exponential function, we have the natural log of x, and then we have our basic trig functions, sine and cosine. And almost, not all, but most functions we encounter in math can actually be created from those 5 functions. Like we might be multiplying them by something, we might be multiplying them by a lot of something, but in general, a lot of the key functions we use in math are based off of those 5. Now, if you go off to college, they might say there's like 6 main series to know or 7 main series to know, but for us, and honestly for me, like those are the 5 that are pretty important. How they'll use these on the AP exam, again, we can't really do much stuff with them until Friday, and we have like a better background on them. They'll say something like, using a known series, blah, 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 blah. And I kind of hate that phrase for it. They'll use the phrase a known series, like everyone should just know them. Clearly looking at that, that is not something that everyone would know. Like it is something you have to like kind of teach yourself and learn. I call them the big 5. College board's going to call them the known series. So I'm looking at the time, 105, we'll probably get through at least 2 of them today, and we'll do the rest of them kind of tomorrow. And again, when we're doing these series, things you want to be able to do with these series for now, you basically want to know the sigma notation, starting point, ending, and kind of like the formula. I would also know the first 4 terms, which if you know the sigma notation, then you should also know the first 4 terms. You can just plug in 4 numbers. And then obviously, like what it's equal to. The first one we have, and again, I know I haven't given you time to write that down if you haven't, we're going to kind of figure it out one by one. The first series you want to know is the geometric one. And we can kind of talk about this one without having to do the formal like Taylor series table with like n, f of n, f to the n, and things like that. Because when you look at that one, I am calling it the geometric kind of formula. Why are we saying, or why are we calling this the geometric power series? What does it look like that we have already kind of discussed? It looks like the geometric sum. So if you remember what we had on the quiz, when we were trying to find the sum of a geometric series, what was that formula? The initial over 1 minus r, as long as, of course, the absolute value of r was less than 1. So how can I convert this into a series? Well, what is the initial term, if you will, that you can kind of get from that working backwards? 1. What's the common ratio? What's the r value? X, and then it's geometric because we're kind of like multiplying by x each time. We're going to start this one at n is equal to 0. All of the special ones are going to start at n is equal to 0 except for one of them. And that's basically what we have. Of course, most of the time, we'll simplify this and not include the 1 in front because that's kind of like a duh. And what does this look like? Well, plugging in 0, we have 1, x, x squared, x cubed, and then that continues forever. So again, what does this mean? The function 1 over x is equal to 1 plus x squared plus x cubed, ad infinitum, plot times x times x times x times x. That's the geometric one. Pretty much all rational functions are in some way related to the geometric one. The other one that I wanted to do is another easy one to figure out, and that is e to the x. So I know you can kind of scroll through and just look at the formula, but go ahead, and you may need to do like not as much, but go ahead and use that Taylor polynomial table and start generating the first few terms of e to the x and see if you can recognize a pattern. So like ultimately you want to memorize the formula, but if you ever forget it, this one is a pretty easy one to start generating terms because e to the x does have a pretty easy derivative. For all of these, again, except for one, we will be centering it at 0. And so that will make the calculations a little bit easier for us. So go ahead, take some time, start generating a polynomial with the ultimate goal of you should be able to notice a pattern you see with like the coefficients and the exponents and things like that. And then once you notice that pattern, use that pattern to see if you can write the sigma notation, and then memorize it eventually. And again, I'm not putting like a limit to what you can find, but find a few, and hopefully you kind of recognize the pattern pretty quickly. So again, I think it's a pretty easy table to see. The derivative of e to the x is always e to the x. Plugging in that center, e to the 0th power is always going to give you 1. So like when you're using that formula, it's always going to be 1 over n factorial times x to the n. So like you're looking at this pattern, we have the terms are like 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. If I wanted to keep going, what's going to be the next term? 1 over 4 factorial x to the 4th. So then memorizing a series, e to the x is the same thing as, what formula will we say for e to the x? X to the n over n factorial. I like separating so there's a clear like coefficient and variable. So 1 over n factorial x to the n. And again, that's something you want to eventually have memorized, that the function e to the x is always in that pattern. If you go back and look at the example that we did that was e to the 2x, it's not the same pattern, but it is one related to that one. Again, all e to the x functions are going to be related. Let's do one more. We'll do the trig ones tomorrow. Try it for the natural log of x. Same thing. Create a Taylor polynomial series for the natural log of x. I will say for the natural log of x, that is going to be our one special one. And for the natural log of x, we cannot center it at 0. Why can't the natural log function be centered at 0? It's undefined at 0, and like it doesn't exist to the left of 0, so 0 can't be the center of anything. So the natural log is the only one that we are going to be centered at x is equal to 1. But everything else will kind of be the same. Create a kind of table. Use as many rows as you need to. Maybe I would go to like the 4th degree. Look for a pattern. Identify kind of the first few terms you have. And then we're going to use that pattern to kind of write a formula for that series. And that's where we're probably going to wrap up today. And once we do that, tomorrow we'll do the trig ones, start kind of working with them, but really get into the juicy stuff on Friday. So again, you should be able to generate those first 3 columns pretty easily. So I just went to degree 4 just so I can kind of see a pattern. Natural log of x is the original function. Its derivative 1 over x, wrote that as x to the negative 1st power, and then just took the power rule over and over again. And I could keep doing that, but I'm mainly just trying to look for a pattern. First term, not so exciting, because you'll have like 0 over 0 factorial x minus 1 to the 0th. Well, that's just all 0. Not so exciting. The first true term you have is going to be 1 over 1 factorial x minus 1 to the 1st, or just x minus 1. Looking at the degree 2, I have negative 1 over 2 factorial x minus 1 squared. And then I can kind of continue that. Next one, I have the 2 over 3 factorial x minus 1 squared. Simplifying that, not squared, cubed. Simplifying that, I'm so excited to simplify it. 2 over 3 factorial. 3 factorial is 3 times 2 times 1. So we know that like the 2 is canceling out, and it ends up looking like this. Looking for that degree 4, I have negative 6 over 4 factorial, x minus 1 to the 4th. Simplifying that one, 4 factorial is 4 times 2 times 3 times 1. The 2 and the 3 cancel out with the 6. We have negative 1 over 4, x minus 1 to the 4th. If I'm looking at patterns, what do I notice is kind of being created for the Taylor series for the natural log of x? It is alternating. So again, if I kind of write out the terms, I think it makes it more obvious. Ignoring the 0, because it is not exciting at all. But this is, we have this x minus 1. I'm going to think about it as 1 over 1, x minus 1 to the 1st, minus 1 over 2, x minus 1 squared. Next term, positive 1/3, x minus 1 cubed. Next term, negative 1 over 4, x minus 1 to the 4th. If you were to keep going with that, what would be the next term you get to?
1/5.
Positive 1/5, x minus 1 to the 5th. So again, what we want to eventually memorize is a series that is the exact same as the natural log of x. I am going to start it at n is equal to 1, since that first term was a 0 and is not exciting, so it really does start when n is equal to 1. Since it is alternating, what needs to show up kind of in the formula? A negative 1 raised to something. We can kind of argue what it needs to be raised to. So I'm going to leave that there for now. There will be an exponent on that in a second. What's in the denominator of each coefficient? Just n. So we can kind of see that's going up by n. The denominators are like 1, 2, 3, 4. It is centered at 1, so I have x minus 1. The exponent is also just n. Those always match. And then we need to figure out what exponent needs to be on the negative 1. Well, I see the first term is positive. The second term is negative. So what should be up there? n plus 1. Because you want to think the first one needs to become positive, so it doesn't become a 2 first. You could say n minus 1, but traditionally we're just going to say n plus 1. So that's where I'm going to stop at today. The last 2 series we'll talk about before we can start doing stuff with it is going to be with cosine and sine. Again, what you ultimately need to be able to have done is those 5 need to be memorized. Like, it's going to help you out the sooner you can memorize them. It looks like a lot, like I know it's a lot, but you can do it plenty of students before you have done it. But those are going to be the ones that we are kind of going to do stuff with and being able to manipulate. Homework-wise, because I'm going to go ahead and end class now, so I'm not rushing it at the end, is so kind of looking at this checklist. At this point, you should be able to basically finish all of homework 7, like you have enough to do that. Should be able to continue working on those quiz corrections if you haven't already. You can also now begin homework 8. Homework 8 I actually have divided onto 2 pages and OneNote, and that's because like the first page is just us generating Taylor polynomials with that table. The second page is you actually using those memorized ones. So I didn't want to kind of put them on the same page. I did want them separated. So basically, short version, you can do all of 7 and the first half of homework 8. I am going to go ahead and end class there for today. Tomorrow when we're virtually, we'll